Hello. This video and the next one are just designed to ease you into the idea of proofs, which are a little bit abstract, I guess, a little bit different from what you're used to doing. In order to create proofs, you're going to have postulates. Axioms, postulates are pretty much the same. These are rules which we state without proof. They're like Ben Franklin's old self-evident truths. We just accept them. And they do kind of make sense. We go through these. For instance, the ruler postulate. Remember, that's the one that says you can measure the length of a line segment. Well, probably no big surprise. This one here says if you break the segment up into parts, the lengths of the parts will add up to the length of the whole. These two say pretty much the same thing, but for angles. This one says you can, in fact, measure an angle. This one says if you break it up, the sum of the angle measures will add up to the original angle measure. Again, probably no big surprise. These are all, again, very simple concepts that I'm sure you don't have any trouble with. For instance, number 5. What does that say? Through any two points, there exists exactly one line. What does that mean? Well, it just means that if you were to draw 2 points, you can always draw a line that goes right, well, some people could always draw a line. There, that looks more like a line. Maybe they should have written it. Well, the line exists. There's exactly one line through any 2 points. Whether you can draw it or not kind of depends on how good you are at drawing. But that's why they invented straight edges. It doesn't work too well when I use a straight edge on the equipment I'm using, but yeah, with pencil and paper, any old straight edge will do. A line contains at least 2 points. That means that if you have a line, you know for sure that there are at least 2 points. Later on, we will determine that there are even more, but at a minimum, it contains 2 points. We can accept that as absolutely true for now. If 2 lines intersect, then their intersection is exactly 1 point. Well, that kind of makes sense too. Let's put another line up here. Well, that one kind of looks like a line, doesn't it? Oh, how are they going to intersect at more than 1 point? I think we already went through this. They won't. Any 3 non-collinear points, there exists exactly 1 point. Well, this is very much analogous to the 2 points form of line. 2 points form a line. Wow. Let me get the marbles out of my mouth. Hang on a second. Okay, they're gone. If 2 lines as I say, this one, the 3 non-collinear points, very analogous to this one up here. Any 2 points forms a line. Any 3 non-collinear points forms a plane. You already know this. And conversely, a plane contains at least 3 non-collinear points. Just like up here, a line contains at least 2. We will find later that it contains more than 3, but it contains at least 3. We know that right now, and we can use that later on when we start proving theorems. If 2 points lie in a plane, then the line containing them lies in the plane. Yeah, sounds good to me. And if 2 planes intersect, then their intersection is a line. And I'm sure you've seen pictures of that. So this is all, well, pretty much makes sense, right? Or to put another way, is there anything in here that you would strongly object to? There's something here that you're pretty sure really isn't true? Well, as an old math prof of mine used to say, you should spend some time sitting under a tree thinking about it. Well, now that we have all these rules in front of us, what we're going to do is solve a few problems. These are going to be pretty simple. Like I say, this is just easing you into the idea of a proof, which is a little more difficult. And if you're using different books, some books don't have these two sections in front of the proofs. They just throw you into the proofs. I don't know which is better or which is worse, but since we have this, I went ahead and made a video for it. If you just want to jump right into proofs, well, you can just skip these two videos. This one's on diagrams. Obviously, it says so right there. The next one will use postulates and algebra. And then we'll put it together into more formal proofs. Those will be, spoiler alert, 2-column proofs and paragraph proofs. But don't tell anybody. I want to surprise them. So let's look at some problems here. Here we're asked to state the postulate which the visual demonstrates or illustrates. In other words, this is a diagram of what postulate. And it's written in the if-then conditional form. So how would you interpret this? Well, I would say, given 2 points, that's our 2 points, then there exists the line connecting those 2 points. And I think that would be postulate number, well, in other words, this right here, given 2 points, and there is a line which passes through those 2 points. That would be postulate 5. So this diagram here is intended to illustrate postulate 5. See? Easy. What about this? We are given a plane. That plane contains at least 3 non-collinear points. Kind of looks like this one, doesn't it? Pardon me. This one here. I say they're simple and then I get them all wrong. The plane contains at least 3 collinear points. I'd say that's what's being demonstrated in this diagram here. See? Easy. Well, if you're not me, it's easy. Okay, here's one way. You could rewrite this postulate as a conditional. If we have 3 non-collinear points, then those points lie in exactly one plane. And you might play around with it a little bit. There might be other slightly different ways to word this, but that's basically it. The next part, well, things like this. Remember when you learned how to diagram sentences, and maybe you're still doing it? It doesn't hurt to do that with these conditional statements either. For instance, we have 3 non-collinear points. We'll call that P. That's the hypothesis. All that. Those points lie in exactly one plane. Then this, well, from here to here, this is all Q. So the original statement is written in the, and let's use our shorthand. P implies Q. In other words, P is, we have 3 non-collinear points, which implies those points lie in exactly one plane. Doing this makes it much easier to produce these 3 things. For instance, the converse. Q implies P. See? It's way easier when you use the shorthand. Now you just retranslate that. Three points lie in exactly one plane. For instance, switching Q and P, we would say 3 points lie in exactly one plane, and they are non-collinear points. And that probably wouldn't be true. Not necessarily true. So that one's false. P implies Q, that must be true. It's a postulate. It's true because we say it's true. And that's all there is to it. Remember when you were a little kid, your parents said, because I said so? Well, that's the way postulates work. They're true just because we say so. What about the inverse? Well, remember that's not P implies not Q. Or, let's say, if we don't have three non-collinear points, then those points don't lie in exactly one plane. Now, I wouldn't say that follows, at least not the way I understand it. Let's see here. Say we don't have three non-collinear points, which I guess would mean that they were collinear. Those points don't lie in exactly one plane. Well, the fact is they may or may not. We don't know. We can't say for sure that they do. They may not. If they're non-collinear, they definitely do. If they are collinear, maybe they lie in a plane, maybe they don't. We just can't say much one way or the other. And the contrapositive is just the inverse of the converse. Remember? So that's not Q. Implies not P. Well, how does that work out? Let's see here. If we don't have points that lie in exactly one plane, then we don't have three non-collinear points. I don't think that follows either. Just because they don't lie in one plane doesn't mean that they're not collinear. Doesn't mean that they're not collinear. Yeah, when you start flipping these around, most of these statements, for instance, not P really doesn't follow from not Q, and on down the line here. So I would say the original statement, of course, is true. It's true because we say it is, and the rest of them don't always hold. Here I'm just going to use the diagram to show an example of each postulate. For instance, a line contains at least 2 points. Use the diagram to demonstrate that. Well, there's a line with 2 points, and that's the only one. Well, not really. We've got, it looks like H is intended to be the intersection here, but I'm not really sure. They didn't draw a point, which means H is probably this line here, this line JK. And none of the other lines are actually, we're not actually showing 2 points on this other line here, so J and K. This line here demonstrates postulate 6. A line contains at least 2 points. What about postulate 7? If two lines intersect, then their intersection is exactly 1 point. Well, that would be this right here. Here they are intersecting, and it's only at 1 point right there. What about postulate 8? Through any three non-collinear points, there exists exactly one plane. Well, let's see here. J, K, and G are not collinear. These two are, but that's okay. All three have to be on the same line to be linear. Pardon me. To be collinear, they would have to be on the same line. To be non-collinear, just one of them has to be off the line. So you could use JKG as a demonstration. You could use KG. Well, we got 4 points here, so pick any 3, I believe, because there are no 3 points that I can see which would all lie on the same line. Unless it doesn't look like the same line to me, it looks like a curve. Well, most any 3 points, I think, would probably be a correct way to look at this. There we have one. We're interpreting a diagram here. Which of these 4 statements cannot be assumed from the diagram? A, B, C. We're just going to go through these one at a time and see. A, B, C, and E are coplanar. Yeah. They're all intended to be right in the shaded spot here. If they were up here or over in this, looking like they're part of this plane, then no. The way they're drawn in, they are intended to be coplanar. Points F, B, and G are collinear. Well, let's let's see, there's F, there's B, and there's G. Well, they could be, but cannot be assumed from the diagram. The diagram did not draw a line through G, B, and F. Like the order, that's kind of weird too. Put the middle one there. If there was a line, F would be in the middle. But this can't be assumed, because they didn't draw the line in. So they may lie on a line, that's just optics. But from the diagram, no, this F could be a bit off. Or B could be a bit off, depending on how you look at it. We already know we can pick any two of these 3 points and draw a line. The question is, will the third point be on that line? The diagram doesn't tell us that for sure. But we can double check. Let's take a look at the others and see if they make sense. HC, remember this? This means perpendicular. Line HC, that's this one. It's perpendicular to line GE. Now, just like with these points, we can look at it and see, well, maybe they're on a line, maybe they're not. It kind of depends on how your eye looks at it. With these, they look perpendicular, but how do we know? Because of this little red right angle they put in there. That's intended to show you they're, in a sense, finishing off the square. They're saying this is the right angle, so when we draw this, that forms. And this little angle in here, that's intended to imply that this line here, HC and GE, are perpendicular. You don't have to interpret the angle here. It's as if they had just written right in here, angle HGC equals 90 degrees. That's exactly what that thing says. So we can assume this from the diagram. So the answer to this is yes, we can assume that. Yes, we can assume that. I would say no to that one. And what about this? Line EC intersects. Well, where is EC? Oh, there it is. There's EC. Intersects plane M. Oh, there's plane M at point C. Well, remember, when a line intersects, we draw it as a solid line on one side of the plane and a dotted line on the other to show that it's passing through the plane and not contained in it. So, these dotted lines are intended to indicate that EC does in fact intersect plane M. And where? Well, the way they've drawn it, this is where the solid line turns into a dashed line. That must be the point of intersection. So, the diagram clearly shows that these three are true. It does not clearly show that this is true. It doesn't show that it's false. It also doesn't show that it's true. We just don't know. Okay, we're going to go through each of these little diagrams one at a time, sort of, and see if they conform to what's been written up here. And this looks complicated. Everything looks complicated if you don't break it down to small steps. I think I've mentioned that before. If I haven't, I'm mentioning it now. In fact, talk to your art teacher if you're taking art. Otherwise, read about drawing. People think art and math are so different, and science, they're all completely different. They're really not. When you have a tough art project, what do? You break it down into smaller projects. If you're going to draw a picture of a horse, you don't just boom, draw a horse all of a sudden. You draw the outline and you fill in the details later. You start with simple things and slowly make it more and more complicated. You don't draw a horse the way a printer would from left to right, or right to left. You start with a detailed nose and then expand the head in full detail until you end up with an entire horse out when you're at the far right of the page. Printers do that. People usually don't. So, an art project is really no different from a math problem. If you can do art, then you can do this. So let's start breaking this down one at a time. We have to find the diagram which shows lines LN, AB, and DC. Well, let's make sure, maybe we can toss one out right away. That has ln, that has AB, and that has DC. This one has those, this one has all of those, and this one has all of those. So far we can't eliminate anything. They all pass that test. They have to intersect at point M. Okay, maybe we can throw one out. Point M, they intersect there, they intersect. Well, shoot. We still got all of them. We have no candidate for rejection yet. How about AB bisecting LN? Well, there's AB and there's LN. Remember these two little marks there? They're both the same, indicating that LM and MN have equal measure. They're congruent. Ringing any bells? That means AB is a bisector of LN. So this one checks. So far. That one's okay up to here. What about this one? There's AB. There's LN. Nope. These might be the same, but we don't know that they are. The diagram only tells us that LN is bisecting AB because they show that these two parts are equal. But that's not the condition we're looking for. We need AB to bisect LN. Here's AB here, and here's LN. Well, looks like it bisects here too. Remember, they don't have to be perpendicular bisectors, just bisectors. And the point where they intersect bisects LN because we got that two little marks right there to show that they are of equal measure. So this one works also. And here, well, once again, we have in fact the opposite of what we were looking for, so we can scratch this one. So up to here we have these two candidates. And our last condition, line DC is perpendicular to line LN. Well, there's DC and there's LN. Not only do they not look very perpendicular, but there is no little red right angle here squaring off the original angle to tell you for sure this definitely is 90 degrees. We don't have that, and therefore we can't say that this angle between LN and DC is 90 degrees. In fact, I'm willing to bet that it's not. What about down here? Here we have DC, and here we have LN, and what do we have here? A little red right angle to imply that these two lines are perpendicular. So we were able to eliminate this one at this point here, and we're left with this C. Well, as I say, this section and the next one are just intended to ease you into the idea of a proof. A lot of what we're doing here is in the category of demonstrating or showing, as maybe you've seen it in your algebra books. Rather than a full-blown proof, they would say, show that this is true, or demonstrate that this is true. It doesn't quite carry the weight of a proof, but it indicates that you're almost certainly on the right track. It's just a little bit easier than a full-blown proof. Well, that's what we're doing, what we just did, and that's what we'll be doing in the next video. That's why they're both going to be kind of short. Yay. The crowd roars. So we'll see you next time for our short video on using algebra, doing just about the same thing we just did